Welcome back, class. In today's video, we're going to discuss reaction mechanisms. So, as we've gone through chemistry, right, you have learned how to write what we know as chemical equations. Now, what these chemical equations actually represent is a chemical reaction, but more specifically, the overall reaction, right? They tell us what we start with and what we end with. But what they don't tell us is the actual steps that it takes to get from reactants to products, right? They show us the beginning and the end, but not the process. And most chemical reactions don't occur in just one simple step, right? That's much too complicated for everything to happen at one time. But what the reaction mechanism is that series of individual chemical steps by which the overall chemical reaction occurs. Now, by knowing the rate law, right? Now, remind you that the rate law is what we talked about in an earlier section, and it describes the dependence on the concentration of the reactants of the rate of the reaction. So it shows the connection between the rate and the concentration of the reactants. And to remind you, right, we talked about the order, zero order, first order, second order. Right? And it shows us this dependency. The other key that we talked about for the rate law is that it must be determined experimentally. So we can't just look at a reaction and write the rate law. We have to do kinetics experiments. We have to come up with it experimentally, such as using initial rates method, etc., that we talked about in earlier sections. But it can help us understand the mechanism. So we're going to go through in the next few slides a little bit of an introduction into how this process might look, or how we can gain insight into the mechanism of a reaction. So let's think, for example, the reaction that's kind of similar to what we've been talking about. It's a reaction of hydrogen plus ICl goes to 2 HCl and I2. Okay. So we have 3 molecules coming together to form 3 other molecules. Now, not surprisingly, this kind of 3 molecules coming together all at once to spit out 3 new products is not likely to happen at any appreciable rate, right, if it happens in one single step. So remember back a little bit to when we talked about the Arrhenius equation and how in order to have a successful collision, right, the molecules have to all combine with enough energy and with the right orientation. Now, that's hard enough with 2 molecules. Imagine 3 molecules having to collide all at once with enough energy, everything in the right orientation, right? You would get a really low reaction rate, right? And so that's not typically what we see happening. The actual mechanism, determined again experimentally, right, based on kinetics experiments, right, shows that we have a 2-step process. We have 1 molecule of H2 combining with 1 molecule of ICl to give one of our HCl's and a molecule of HI. And then we have that HI that's produced in the first step combining with the second molecule of ICl that's shown in our overall process to give us our second molecule of HCl and the molecule of I2 that is shown in our overall process. Now, these individual steps are known as elementary steps. And that just simply means these are the actual steps that occur, right? These are the actual molecules that are physically colliding as part of this process. They can't be broken down into any simpler steps. So let's look a little bit more in detail into this mechanism. So, a couple of things that need to be true about a mechanism. So, first of all, the elementary steps must add together to form the overall process. Right? So we have to be able to physically add together the steps to get to here. So if we just illustrate that quickly with this example here, we can see if I group all of my reactants here, I have H2 plus ICl plus HI plus ICl, and I group all of my products. I have HCl plus HI plus HCl plus I2. Now, if we do some grouping and cancellation, right? So we're not going to show the same species on both the reactant side and the product side. So anything that appears on both sides, we can cancel out. So that's going to principally be HI. And we can also do some grouping. So the fact that I have 2 molecules of ICl here means I can group them together. 2 HCl I can group together. And if I rewrite this, what do I get? I get H2 plus 2 ICl goes to 2 HCl plus I2, right? Which matches my overall process. Right? So one of the things that's key if we're going to write a mechanism is that the steps, the elementary steps, have to add up to the overall process. Now, a couple of things to point out here is that notice the HI. HI doesn't appear in the overall reaction, but it's produced as part of the first elementary step and used up, in this case, in the second elementary step. This is what we know as an intermediate. So reaction intermediates are materials that are produced in an earlier mechanism step, but then are used up in a later step. These are called intermediates. Right? And so for this reaction, HI would be what we know as an intermediate. Doesn't appear in the overall reaction. It's produced in one step, used up in a later step. Now, I talked about the low odds of having 3 molecules come together all at once with the right energy and the right orientation to produce products. Well, we talk about this in terms of the molecularity of the collision, right? So we think about these elementary steps, we can give them what we call a molecularity. So a unimolecular step would mean one particle is involved, or one species on the reactant side. We have a bimolecular step. This is when two molecules or 2 species come together, collide, produce products. A termolecular would be 3, right? And notice these are exceedingly rare. Now, these are the most common here. Now, remember, bimolecular, it doesn't have to be 2 different. It could be 2 of the same, right? So we could have 2 H2 molecules coming together, or 2 whatever, coming together to give some other product. So molecularity. Now, let's look back at these elementary steps again. Now, one of the things that I stressed early on when we were talking about the rate laws is that the rate law of an overall reaction must be determined experimentally. You cannot look at the balanced equation and write the rate law. Now, on the other hand, for an elementary step, the rate law of the elementary step can be deduced from the equation. Now, why is this possible? Well, remember, the elementary steps represent the actual collisions that are taking place. They represent the actual events. Whereas the overall reaction, remember, is not an actual step, right? It is a summary, if you will, right? It's the overall process. It doesn't give us the step-by-step detail. So, while we can't write a rate law for an overall reaction, we can write rate laws for elementary steps. And so, each of these elementary steps will have its own rate law, its own activation energy, as we said here, and we can deduce the rate law. We could calculate the activation energy if we wanted to, if we could isolate this step, but the key is that they have an activation energy. So let's just look at these. So let's look at the first one. So the first one has 1 molecule of H2 plus 1 molecule of ICl. So what that means is that it's first order in H2 and first order in ICl. So we could write that rate law just like this, right? The rate of this elementary step is going to equal its rate constant times H2 to the first order, ICl to the first order. Now, we can do the same thing with the second elementary step. It involves 1 molecule of HI, 1 molecule of ICl, and so the rate law for this step is the rate of this step equals its rate constant times HI to the first order, ICl to the first order. So, bottom line is we can write these elementary steps. Now, what does this do for us, So we can write them. That's great. But we're going to talk about that in a couple of slides. But first, let's kind of summarize this. So, if you want to write this for any elementary step, so if you're given a mechanism and you're told this is the elementary steps, this is how you can deduce the rate laws. So if you have a unimolecular, right, so only one molecule involved going to products, well then of course it's going to be the rate equals the rate constant times A to the first order. If you have two of the same going to products, bimolecular, right, it's going to be A to the second order in this case. If you have two different ones like we had in the previous ones, right, it's going to be first order in each of those, right? And these are going to be your most common. Now, these are examples of termolecular, really rare, right? You could have 3 of the same, you could have any combination, 2 and 1, 1 and 1, 1, and you would write the corresponding rate laws where the number of molecules of that species represents the order of that species in the rate law of that elementary step. Okay, so we can look at a mechanism, we can write the rate law for the elementary steps. We should be able to do that. Okay, so let's look at another idea about mechanisms. Now, in all processes, in all multi-step processes, there is a slow step, right? There is the step that sort of hinders the overall process or slows down the overall process and sort of in essence controls how fast the overall process can occur. So we can use, examples from normal life, right? So if we have, a manufacturing process and, we can do all these things really fast, but there's one slow step that we have to get just right. Maybe it's, machining a really particular part, or maybe it's some sort of computer-based, programming or whatever. So there's one step in the process that takes longer than all the rest. That's going to be the slow step. That's going to determine how fast we can get through the whole process. So we might be able to go really fast up to that point, but then we have to get through that point in order to get to the end. Or maybe the slow step is, in the beginning. Maybe we have to, it takes a long time to get this thing started or get the process going with that first sort of initial step, and then everything is sort of smooth after that. Well, we can only get to the end as fast as we can get through that first step. Now, in a chemical idea, in a mechanism, that slow step, that step that has the big activation energy, right, that is, challenging, if you will, from a chemical standpoint, that's what we call the rate determining step of the mechanism, or what's sometimes abbreviated as the RDS. So the slow step of any reaction mechanism is what we call the rate determining step. Now, it's going to be the step, not surprising, with the largest activation energy, right? That's what's making the step slow, right? Because it's hard to get over that initial barrier to get to products. And of course, the rate and the rate law of that rate determining step will determine the rate of the overall process. Now, I just put this picture in because that's what they use in the book, that this is, like if you're making a trip and there's a slow part to your trip. So maybe there's construction on, one part of I-80 or 380 or wherever we're going to be going, right? We can be really fast, but then we get stuck in that slow traffic, and it determines how fast we can get to our end point. Okay, so this concept of rate determining step is a big idea in mechanisms. So let's look at a mechanism here. So here's another mechanism. So this mechanism, we're looking at the reaction of NO2 plus CO goes to NO plus CO2. Now, this has an experimentally determined rate laws. That's why we say it's observed, right? So we've done some kinetics experiments, and this has been experimentally determined. Now, a mechanism, or let's call it a potential mechanism for this reaction, is as follows. This two-step process of two molecules of NO2 coming together to give you NO3 and NO, and then NO3 combining with CO to give you NO2 plus CO2. So, we can take these elementary steps, we can write a rate law. So, we get the rate equals NO2 to the second order. Right, we got two molecules. Second step equals NO3 to the first order, CO to the first order. Okay, so let's look at this. So first of all, the first thing we can always do is, if we're trying to decide whether a mechanism is potentially the correct mechanism, is see if it meets the first criteria, right? Which means it has to sum up to the overall process. So let's look at this. If we sum all of the reactants, we get, and I'm just going to go ahead and group them, right? We have two NO2s, so I'm just going to go ahead and do that just to save us a little space. Plus NO3 plus CO. And we have our products. We have NO3 plus NO plus NO2 plus CO2. Again, we can go through our grouping and our cancellation. Notice we have NO3 being produced in the first step, used up in the second step, right? So we can cancel it out. That's going to be our intermediate, or it's going to be an intermediate in this process, right? So if we wanted to label the reaction intermediate, NO3 would be what that is. And then we also have NO2 on both sides. So we have two molecules here, one molecule over here. So we can cancel out one of those on each side, right? So our overall process is going to be, when we write our overall reaction, it's going to be the simplified, right? We're not going to show same materials on both sides. So we finished out the cancellation, so let's summarize this. So we have NO2 plus CO goes to NO plus CO2. And of course we can look up and see if that matches. And yes, it does, right? So all that tells me is that this potential mechanism is valid, right? It is let's use that word a different way, but it is a possible mechanism, right? Because the steps add up to our reaction. Now, another key part of reaction mechanism problem is because we're not doing these reactions, right? We're just taking data that other people would have determined. One of the things that they have to tell you when you go to analyze a mechanism is they have to tell you the slow step. So by telling us that this first step is the slow step, in other words, this is the rate determining step. Okay, so they've told us that. Now, we can show this in picture form, right? By showing our mechanism here. So this is again one of our energy diagrams or our reaction diagrams. And so we've broken out, instead of having just an overall reaction, we've now broken down to individual steps. So you notice we have two activation energies. We have the first step, which has a bigger activation energy. And we have the second step, which has a lower activation energy. And then we go down to the product. Okay? So this clearly here, right, with the biggest activation energy, this is going to be our slow step. Now, because it's the slow step, it's going to determine the rate of the overall reaction. So step one is going to determine the overall rate. Right? Now, if we have a proposed mechanism that has the slow step as the first step, then it's pretty straightforward to give what the rate law of that mechanism would be. So if the first step is the slow step, so I'm going to write this out down here just so it's clear. If the first step is the rate determining step, then the rate law for that step is the rate law of the proposed mechanism. So if the first step is the rate determining step of our proposed mechanism, then the rate law for that step will be the rate law of that proposed mechanism. So for this proposed mechanism, since the first step is the slow step, this would be the rate law of the proposed mechanism. So the second step, or the second criteria, in order for a mechanism to be a potential mechanism for a process, is that the rate law of the proposed mechanisms must be the same, must equal the experimentally determined rate law, right? So we already know what the experimentally determined rate law. So if a potential mechanism is going to be the actual mechanism, then the rate law of that proposed mechanism must match the experimentally observed rate law. And in this case, of course, they do, right? These are the same. So all what that tells us is that this potential mechanism here is what we call a valid mechanism for this process. Now notice I say it's a valid mechanism. It doesn't tell us it is the mechanism, right? We can't absolutely say that this is the mechanism unless we can physically observe what's happening. But what we can do is we can come up with a bunch of evidence to support a mechanism. And we can say that this is a valid mechanism. And we can come up to support the supportive evidence of that valid mechanism, because there can be more than one valid mechanism. And other information, other experimental data can help us decide which of these proposed mechanisms, these valid proposed mechanisms, is maybe the actual mechanism. All right, so let's summarize what we call the steps of validating a mechanism. So in order to validate, again, not prove a mechanism, that proposed mechanism must meet two steps. So the first one that we've talked about is the elementary steps must add up to the overall reaction. So we did that a couple times, right? And we just take all the reactants, all the products, cancel out materials that appear on both sides, reaction, whether it be intermediates or, simplifying, and it has to match the overall process. The second one is the one that we just talked about. The rate law predicted by the mechanism must be consistent with the experimentally observed rate law, right? So the one that we've done the kinetics experiments and shown. All right, so that's a little bit of mechanisms. I'm going to do a little bit of an example problem here following this. Now, I will point out that in the book, there are a different kind of mechanisms that are talked about where the slow step is not the first step. I won't really be working with those or asking you to do those. The goal here is not to get so deep into this idea of mechanisms at this point in your chemistry study, right? So I'm going to stick to ones where we have a first step as the slow step. All right, so I'm going to do that problem here, and then in the next video, we're going to talk about catalysis.